11,500 feet is the minimum elevation where the oxygen thinness and freezing temperatures of the Himalayas begin to dictate the terms of human survival. At this altitude, the population was once forced to rely exclusively on a single mountain pass known as Zojila to maintain any connection with the outside world. Why did a few hours of heavy snowfall pose such a catastrophic threat to the entire regional infrastructure? One might assume that standard snow removal equipment could clear the path. But in reality, the sheer volume of winter precipitation caused the only available route across the jagged peaks to vanish from the transportation map for months at a time, resulting in the total isolation of the territory on the opposite side. Modern engineering has opted for a significantly bolder strategy than merely accepting seasonal seclusion. Engineers are currently driving a path directly through the ancient rock of the mountain range to bypass the treacherous surface conditions. 8.7 miles is the total length of the Zojila Tunnel, a massive subterranean passage excavated deep beneath the Himalayan crust. The project aims to ensure that vehicular traffic remains in motion 365 days a year, regardless of the accumulation of ice, the sudden movement of landslides, or the occurrence of extreme weather patterns. But this is just the beginning. The camera glides along the frozen slopes where the construction of the Zojila Tunnel represents a victory over one of the most geologically volatile terrains on the planet. One can notice how heavy machinery operates against a backdrop of sheer cliffs and shifting shale. It is visible how the specialized equipment gradually penetrates the rock face, working within a technical framework designed to preserve vital supply lines in all weather conditions. Everything only gets more complicated as the depth of the excavation increases. Thousands of tons of granite and debris are removed from the heart of the mountain to create this permanent corridor. This technical feat required the development of specific structural reinforcements to withstand the immense pressure of the Himalayan mass overhead. The process concludes this phase, opening the road to a permanent connection that defies the seasonal cycles of the high altitude. 11,575 feet is the extreme elevation where the Zojila Pass sits amidst the jagged peaks of the Himalayas. Why is this specific point in the mountain range considered one of the most dangerous transit corridors in the world? It would seem that a simple mountain road could suffice for regional travel. But the winding path of the pass serves as the only viable lifeline connecting the Kashmir Valley with the Ladakh Plateau, two territories divided by starkly different geological and climatic systems. For many decades, this narrow strip of asphalt remained the sole artery for the transport of essential goods, fuel supplies, and military personnel to the remote Ladakh region. But this is just the beginning. The equipment gradually becomes buried under massive drifts as snow blocks the pass for 5 to 6 months every single year. One can notice how the landscape transforms into an impassable white barrier, leaving the entire Ladakh region in a state of near total isolation during the harsh winter season. At first glance, the geography seems insurmountable, but in reality, the strategic necessity for a permanent link forced a massive engineering response. To eliminate this seasonal bottleneck, India initiated the construction of the Zojila Tunnel, a monumental subterranean passage stretching approximately 8.7 miles in length. Thousands of workers operate day and night within the dark confines of the mountain. The process is only gaining momentum as crews drill deep beneath the Zojila Pass into a rock mass that is 45 million years old. Because the elevation is so extreme, the atmosphere contains significantly less oxygen, forcing personnel to work in severely oxygen-deprived conditions. It is visible how freezing meltwater from ancient glaciers continuously seeps through the stone, creating a constant struggle against the elements inside the tunnel. $1 billion is the total investment required to realize this two-lane road project. The camera glides along the reinforced concrete walls designed to withstand massive landslides and temperatures that plummet far below the freezing point. This infrastructure does not merely serve as a path. It reduces a treacherous 3-hour climb to a controlled 20-minute transit. Transition to the next level. The tunnel establishes a state of permanent year-round connectivity that was previously impossible. Such a massive technical achievement reshapes the geopolitical balance along the northern frontier of South Asia by strengthening logistics and national security. It only looks obvious to call this a road, but in reality, it is a strategic asset of immense importance. The material and structural integrity of the tunnel ensures that snowstorms no longer dictate the movement of people or supplies. Thus, the project concludes the era of seasonal isolation, opening the road to a stable and connected future for the high-altitude plateau. 11,500 feet is the exact elevation above sea level where the construction of the Zojila Tunnel takes place. Why is building at such an extreme altitude considered one of the most difficult engineering feats in the world? It would seem that standard tunneling equipment could simply begin boring into the rock as it does in any other mountain range. But without a completely specialized life support infrastructure, the human body and heavy machinery would fail long before the first mile of rock was cleared. Oxygen levels in the thin Himalayan air drop to only 60% of the concentration found at sea level. This physiological barrier directly limits the physical output of every person on the site. But this is just the beginning. The camera glides along the perimeter where temperatures frequently plummet to -4 degrees Fahrenheit or lower. Heavy snowfall and gale force winds create a physical wall of ice that leaves the entire geography isolated for several months of the year. One can notice how the equipment gradually becomes encased in frost if left stationary for even a few minutes. Engineers did not start the project by drilling into the mountain face. It only looks obvious to begin with excavation, but in reality the first critical phase was the construction of a self-sustaining survival environment. Highly insulated prefabricated structures were assembled to house the workforce. These units are not merely shelters, as they are equipped with integrated heating systems, a supplemental oxygen supply, and specialized medical clinics. Medical staff monitor the health of every worker, specifically for altitude-related complications. The process is only gaining momentum. Work shifts are organized into short rotating cycles rather than the long-term rotations typical of lowland industrial sites. This allows the biological systems of the workers to adapt to the thin atmosphere and extreme cold. It seems simple to keep a site running around the clock, but in reality, human endurance at 2 miles above sea level requires a complete restructuring of labor logistics. Independent power generation stations operate ceaselessly to provide a dedicated electricity supply for the entire complex. One can notice the steady hum of these generators, which remain separate from the regional high-altitude power grid. Because the local infrastructure is not reliable enough to support a project requiring 24/7 operation, these autonomous units serve as the heartbeat of the site. Transition to the next level. The equipment is fueled and the living quarters are pressurized against the harsh Himalayan elements. Thus, the foundation for the long-term survival of the project is established before the primary drilling begins. 150 million years of geological history define the immense tectonic pressure exerted on the Zojila Tunnel project. Unlike many modern tunnels in Europe or East Asia, where massive tunnel boring machines can operate continuously through relatively stable rock formations, this alignment runs deep within the geologically young Himalayan mountain system. Why is the use of automated boring machines deemed far too risky for this specific corridor? The rock layers here are under constant stress from the ongoing collision of tectonic plates, creating a landscape where solid, intact rock can abruptly shift into fractured zones or weakly layered strata within a very short distance. One can notice how groundwater influences these heavily weathered zones, making the geology unpredictable. A single unexpected change in rock strength or ground pressure could trap a multi-million-dollar machine deep inside the mountain. Therefore, the Zojila Tunnel project adopted a more flexible construction approach to avoid a prolonged standstill. Engineers drive the tunnel in small, incremental steps, allowing them to adjust their methods in real time based on the actual conditions discovered inside the mountain. It seems simple to just dig through, but in reality, every meter requires a new assessment of the surrounding mass. The process is only gaining momentum. The excavation cycle begins with drilling small holes into the rock face ahead. Based on survey data and direct on-site observations, the location, depth, and angle of each drill hole are carefully calculated. This ensures that the rock breaks precisely to create a new tunnel face while maintaining the structural integrity of the mountain. One can notice the slow, methodical movement of the drilling rigs as they penetrate the dense strata. Controlled blasting follows the drilling phase using carefully measured amounts of explosives. The detonators are not triggered simultaneously, but in a very rapid sequence, separated by only a few milliseconds. This millisecond delay technique helps limit vibration transmission and reduces the risk of destabilizing the tunnel roof and sidewalls. But this is just the beginning of the cycle. High-capacity ventilation systems activate immediately after each blasting round. These units extract blast fumes, rock dust, and toxic gases from the confined, oxygen-depleted environment of the high-altitude mountains. It is visible how the thick clouds of dust are drawn out to ensure air quality, which is strictly a matter of survival for the crew. Only after monitoring instruments confirm that conditions are safe are workers allowed to re-enter and resume operations. The fragmented rock produced by the explosion is cleared to expose the new tunnel face. Temporary support measures are installed immediately to stabilize the roof and sidewalls, preventing any further movement of the surrounding rock mass. Transition to the next level of the operation involves organizing the project to excavate simultaneously from two opposite tunnel portals. This dual portal approach allows for a flexible allocation of manpower and equipment while accelerating progress whenever the mountain permits. 9 feet per day is the average distance each excavation face advances. At first glance, this figure may sound modest for such a large-scale project. In reality, under the complex geological conditions and harsh environment of the Himalayas, this is a carefully calculated pace designed to ensure the safety of every person on site. It gets more complex further on as the tunnel segments are linked together. Every completed section of the tunnel is the result of close coordination between engineering and on-site experience. The equipment gradually moves forward, marking the continuous adaptability of human effort in one of the most challenging construction environments in the world. The material is cleared and the support structures are locked into place, allowing the project to move to the next phase of the production chain. Thus, the steel and rock reach a state of equilibrium, ready for the further stages of the long-term construction plan. 150 minutes is often the maximum window allowed for stabilization before the mountain begins to reclaim the void. Why is the interval between excavation and support so strictly regulated in the Himalayan range? The geological pressure here is unpredictable, and leaving a freshly exposed surface without reinforcement risks a sudden structural failure. If the rock face remains open to the atmosphere for too long, even a minor vibration or a shift in groundwater pressure can trigger deep cracking or a localized roof collapse. Therefore, the stabilization of the tunnel surface is a mandatory operational phase that begins almost immediately after the completion of every excavation cycle. The equipment gradually moves into position to initiate the primary defense. One can notice how high-pressure nozzles spray fast-setting shotcrete directly onto the entire newly formed rock surface. Because of the low-temperature environment typical of high altitudes, the chemical design of the concrete mix and its setting time are adjusted with jewelry-like precision. This ensures the material achieves sufficient load-bearing strength within a very short period to counteract initial decompression. But this is just the beginning. It seems simple to just coat the surface, but in reality, the internal rock mass requires deep structural integration. Long steel rock bolts are drilled deep into the surrounding geological layers to anchor fragmented sections together. This process creates a stable composite structure and redistributes the massive stresses generated during the blasting phase. The equipment operates with a steady rhythm, driving the steel rod's meters into the solid stone. Everything only gets more complicated when the team encounters sections of weak geology or zones with a high risk of water ingress. In these specific areas, steel support ribs are installed in a precise arched configuration to serve as additional heavy reinforcement. It is visible how these massive frames preserve the tunnel shape against the immense weight of the mountain above. The combined application of shotcrete, steel bolts, and arched ribs allows the team to control structural stability meter by meter. This technical synergy transforms a space freshly disturbed by explosives into a structure secure enough to permit further advancement. The process is only gaining momentum as the excavation pushes deeper into the constantly changing geological environment. Thus, the newly reinforced section reaches a state of temporary equilibrium, allowing the transformation to move to the next phase of processing without haste. 32 degrees Fahrenheit is the critical threshold where liquid water transforms into a destructive force within high mountain tunnels. Why is the presence of groundwater and melting ice considered a silent threat to the structural integrity of the Zojila Passage? It only looks obvious that a mountain is a solid barrier, but in reality, the alignment of this tunnel runs directly beneath massive Himalayan glaciers and rock layers that have been heavily fractured by tectonic activity over millions of years. This positioning creates a constant hydrostatic pressure against the engineering works. Water penetrates the site through more than just visible streams. It seeps with relentless persistence through countless microfractures in the surrounding stone, gradually working its way into the concrete mass where it accumulates over time. One can notice how moisture beads on the rough surfaces before the final lining is sealed. But this is just the beginning. As the external temperature drops below the freezing point of 32 degrees, the trapped liquid begins to expand in volume. The equipment gradually records the internal pressure generated within the concrete structure during these transitions. Everything only gets more complicated as the seasons change. Repeated freeze-thaw cycles occur dozens of times throughout the year, leading to concrete cracking, the spalling of surface layers, and a progressive loss of the tunnel's load-bearing capacity. This degradation directly threatens the long-term durability and safety of the passage through the mountain range. For this reason, drainage and waterproofing systems are implemented in parallel with the excavation and surface support works. It seems like a simple task to manage moisture, but in reality, it requires a dual-layer defense strategy. The process is only gaining momentum as the tunnel advances deeper. Seeping water is collected immediately at the tunnel invert, where it is captured by gravity and channeled out through dedicated drainage pipes at a controlled flow rate. The camera glides along the curved walls, where waterproofing layers are installed to act as a physical barrier. This shield prevents groundwater from penetrating deeper into the primary structural lining of the vault. One can notice how the synthetic membranes are welded together to form a seamless envelope around the hollow space. Transition to the next level of protection involves the integration of these layers with the permanent concrete shell. This combined engineering approach allows groundwater to be controlled at an early stage of construction. It ensures that the tunnel remains stable and operational, despite the harsh freeze-thaw conditions characteristic of the high Himalayas. The drainage network functions ceaselessly to maintain the equilibrium of the structure against the weight of the glaciers above. The material is ready to move to the next processing phase without haste. 13 kilometers of underground passage reach their final structural form once the primary excavation and stabilization of the Zojila Tunnel are concluded. Why is the construction of the tunnel invert considered the most critical transition point in this sequence? At first glance, it is merely a floor, but in reality, this structural layer serves to lock the geometry of the entire cross-section and carry long-term loads while providing a permanent foundation for every technical system installed above. The foundation must withstand the immense pressure of the Himalayan rock mass for several decades. Construction crews move with calculated precision to secure the base of the mountain passage. The transition from an active construction site to a continuously operating infrastructure system marks a shift in the project's core focus. One can notice how the focus is no longer on advancing additional meters through the rock, but on ensuring the internal space remains safe and reliable. The entire tunnel surface undergoes comprehensive waterproofing to prevent groundwater and meltwater from penetrating the reinforced structure. This barrier is essential to mitigate the risks of freezing and corrosion under the harsh climatic conditions of the high-altitude range. The equipment gradually transforms the dark cavern into a functional corridor. A specialized lighting system is installed along the full length of the tunnel, designed to operate without failure in damp, cold, and dusty environments. These fixtures do not only support standard traffic operations, but they also maintain the necessary visibility for inspection, maintenance, and emergency response teams. It gets more complex further on. The ventilation system undergoes a total upgrade from its temporary construction mode to a permanent operational state. This involves the installation of high-capacity fans and fixed ducting systems. Automated control units adjust the airflow based on real-time traffic density and internal atmospheric conditions. Safety sensors form a dense network throughout the passage, continuously monitoring air quality and the concentration of toxic gases. Temperature, smoke, and other abnormal indicators are tracked with every second that passes. All collected data is transmitted to a central control center for constant supervision. In the event of a fire, the ventilation system can rapidly reverse its airflow to extract smoke while creating a safe corridor for evacuation. Surveillance cameras and emergency communication systems are positioned at precise intervals along the rock walls. These allow for early incident detection and provide direct guidance to vehicles during emergency situations. The process is only gaining momentum as the various subsystems are integrated into a single mechanical organism. It is this specific combination of durable structural works and proactive technical systems that has transformed the excavated space of the Zojila Tunnel into a year-round transportation corridor. The mountain has been tamed by engineering, allowing for reliable operation regardless of the extreme weather conditions outside. The structural phase concludes, opening the road to final commissioning and use. 14 kilometers of mountain rock are being pierced by the Zojila Tunnel project, proving that this is far more than a standard transportation route across a range. Why must engineers invest such immense resources into a single subterranean passage? The environment here was never physically intended to host modern infrastructure or human transit. Without this extreme level of structural intervention, the geological forces and climatic extremes would reclaim the path within a single season, rendering any traditional road useless. Engineering begins with the human element. One can notice how specialized modular units are established to create temporary living conditions for hundreds of technicians and laborers in the frozen isolation. This phase focuses on survival as much as construction, with massive ventilation fans circulating air to manage atmospheric quality and internal temperatures deep within the rock face. But this is just the beginning. Hydraulic drills bite into the stone with jewelry-like precision to prepare for controlled detonations. It only looks obvious to blast through a mountain, but in reality, every explosive charge is calculated to prevent unintended collapses in the unstable strata. The process is only gaining momentum. The equipment gradually installs heavy steel ribbing and layers of sprayed concrete to reinforce the cavernous walls immediately after each blast. These structural systems are designed to withstand the immense lithostatic pressure of the peaks above. At first glance, the task is about removing rock, but in reality, it is a constant battle to stabilize the remaining shell. Everything only gets more complicated. One can notice the camera glides along the intricate networks of long-term operational systems being integrated into the tunnel lining. These include drainage channels to prevent freezing and advanced sensors to monitor structural integrity in real time. This transformation serves a single, unyielding purpose. It turns a route that was historically blocked by heavy snow for several months every year into a reliable year-round transportation corridor. Modern engineering redefined the movement of people through the harshest mountain ranges on Earth. The material and the mountain are now locked in a permanent managed state of coexistence. This concludes the phase of initial penetration and stabilization, opening the road to final paving and lighting. 11,575 feet above sea level is the elevation where the Zojila Pass imposes its harshest challenges upon the Himalayan landscape. Why would engineers attempt to penetrate one of the most formidable mountain ranges on Earth with a permanent tunnel? The existing pass remains buried under thick layers of snow for nearly half of every year, effectively severing the connection between Ladakh and the rest of the world. By driving a massive concrete artery straight through the ancient rock, modern engineering provides a definitive answer to these environmental constraints. One can notice how the mountain face is systematically carved away to accommodate the flow of heavy machinery. Modern engineering chooses to bypass the unpredictable surface conditions rather than accepting the seasonal isolation dictated by nature. The Zojila project functions as a primary catalyst for the evolution of the regional transportation map, fundamentally reshaping the methodology humans use to approach the world's most rugged and vertical terrain. It is visible how the heavy excavators move with calculated precision to clear the debris from the tunnel mouth. But this is just the beginning. The tunnel represents a single critical link in a sprawling chain of massive infrastructure works designed to conquer high altitudes. Engineers choose to cut through high mountains and span deep valleys with bridges that seem to hover in the thin air of the peaks. Building such infrastructure in locations once considered impossible requires a constant sequence of drilling, blasting, and structural reinforcement. It only looks obvious to connect 2 points on a map, but in reality, every meter of the tunnel is a struggle against geological pressure and extreme cold. The process is only gaining momentum. Infrastructure of this scale ensures the uninterrupted movement of logistics and essential supplies throughout the entire year. the camera glides along the massive reinforced walls where thousands of tons of rock are held back by steel and concrete. At first glance, the tunnel appears to be a simple corridor, but in reality, it is a complex life support system for an entire region. The Zojila Tunnel allows the transition from a seasonal mountain trail to a high-capacity industrial route. This massive undertaking brings a sense of permanence to a landscape characterized by constant shifts and landslides. From here, the finished passage moves toward its operational phase, securing a stable future for the Himalayan transportation network.